All right, so we talked about intercepts, we talked about predicting and behavior, and we've also talked about multiplicity, right? So the whole reason why we talk about intercepts is because intercepts can actually provide us really key information about how our polynomial is moving. And so, like we've been saying before, right, this allows us to rely less heavily on tech and develop intuition about what our polynomial looks like and how it behaves. So a bit later in our lesson, so in the next video, when we talk about derivatives, we'll develop a definition of how x-intercepts of derivatives are called critical points and what they tell us about our polynomial. But before we can do this, we need to start developing some language regarding polynomial shape and behavior, and this is kind of the crux of calculus, and so this is really important that we get this notation down. So whenever we talk about end behavior in functions, or just behavior in functions, we talk about it through something called limit notation. So just like in other forms of math, in calculus we use shorthand to get across big ideas. And one major idea we use is limits. So limits tell us where a variable's heading, right? So in calculus, as our variables grow larger and larger, we always approach values, right? Our evaluations are extremely precise approximations. So this is saying if you're going towards x equals 1.5, right, you're not actually hitting 1.5, you're getting infinitely close to 1.5. So you're actually looking at really, really, really small numbers and kind of approximating and giving us a general idea of where we're going. So when we're talking about limit notation, there are a few different parts, right? So let's just break it up into different parts, right? So we have our f of x component and we have our x component. So we can look at how our x is going to behave and how our y is going to behave. So if we're given this notation, right, f of x arrow infinity, right, this means that your y values, so let me change this, y values are getting infinitely positively large. I don't know why my pen is acting that way, right? Large, okay. Okay, so when we're given this notation, f of x arrow infinity, we read this as f of x approaches infinity. So it's approaching positive infinity. And we've seen this before when we've graphed f of x equals x squared, right? We see that x squared approaches positive infinity as you keep going further to the right. And so on the other hand, if we see f of x arrow negative infinity, this means that our y values get infinitely negatively small, right? Because the further into the negative you go, the smaller your number is, right? And so we can read this similarly as f of x approaches negative infinity. And we've seen that before for the left end behavior for f of x equals x cubed, where we keep going down into the negatives. So we talked about how we can talk about y's. It's the same for x's. And so if we were to put this all together, if we were given the statement as x approaches infinity, f of x approaches infinity, right? In calculus, we would use limit notation. So that statement translated in limit notation, right? We write lim to indicate limit. And then underneath our limit, we write our x behavior. So as x approaches infinity, so x approaches infinity, right? And then we write the function that we're talking about, f of x, and we state what is the limit going to be. So where are we approaching when x approaches infinity, right? And so we set this equal to whatever our f of x behavior is. So we're approaching infinity, so we set this equal to infinity. So this is saying that as your x continues getting positively infinite, right, our y can be approximated as also becoming positively infinite. All right, so let's talk about end behavior using limit notation. So whenever we're talking about limit notation over here, right, we're just going to generally talk about as x approaches positive infinity. But for this specific example, we'll also talk about x approaching negative infinity, because you can look at the end behavior in the other direction, right? So if we're talking about the right end behavior, then x is approaching positive infinity, right? So the limit as x approaches infinity, positive infinity of f of x, and then that just asks us what is the right end behavior, right? And so when I look at this graph for this function, right, I see that I'm approaching positive infinity, right? So this is just going to equal positive infinity. No need to put the positive sign. If I'm exploring the left end behavior, the way that I can write it in limit notation is instead of x approaching positive infinity, where we're constantly going to the right, we're going to go to the left. So x is approaching negative infinity. And then same thing, f of x. And then we want to describe where are our y values heading when our x is approaching to the left, right? So we see that our left end behavior, we're approaching negative infinity. So we would say that this equals negative infinity. So let's look at another example, right? So once again, I'm going to explore the right end behavior. So I have limit as x approaches positive infinity of f of x. And when I look at this graph, right, I see that my right end behavior, I'm approaching positive infinity, right? So my limit is going to be positive infinity. Let's explore the left end behavior. I have x is approaching negative infinity. Okay. And so my left end behavior, because I'm going constantly further down into the negatives towards the left, right, I'm approaching negative infinity. All right, so you have these two practice problems, right? Work on these, pause the video here, and then when you're ready to go over it, let's go over it, right? So hopefully you notice that the way that these practice problems are structured is a little bit different than the way that we've been looking at it in our examples, right? Because in our examples, I gave you the graph for the function, and in this case, it's asking you to look at the graph, right? Another thing that we can do is we can just kind of substitute in a really big number and see, where is our function heading, right? So for f of x equals negative 2x to the 6th power plus 5x plus 4, right? We see that the limit as x approaches infinity of f of x, right? You can graph this, right? But let's say that you don't have decimals in front of you, or if you don't have your graphing calculator, you can still figure out this limit, right? Let's say that we're going to substitute in a billion over here for x, right? A billion's really close to positive infinity, right? It's going super far into the right for our x's. So if we substitute in a billion here, right, this is going to be negative 2 times a billion to the 6th power. So that's going to be a positive value times a negative value. That's going to be a negative value. Plus a positive value times a positive value, that's going to be a positive value, plus 4. But because this is a greater degree, this is actually going to be dragging it down to the negatives, right? And so because this is dragging it down into the negatives, this is going to go down to negative infinity. And that makes sense, right? Because our leading coefficient is negative, so we're pointing down. We also want to notice that the degree of this polynomial is even, right? So we know that the left end behavior is going to be the same as the right end behavior. So your limit as x approaches negative infinity is also going to be negative infinity, right? Whatever your right end behavior is, it's going to be the same as the left, right? Over here, I see that I have a positive leading coefficient, right? My positive leading coefficient tells me that I'm actually going to be approaching positive infinity, right? And I can actually just double check that by substituting in like a billion for x. And so if I substitute in a billion, this is going to be a super positive number. This is going to be negative, but it's going to be a smaller negative number than this positive number here because of the degree. This is going to be positive. This is going to be -1. That's non-consequential at that point, right? So this is overall going to be approaching positive infinity. And then because it's an odd function, right? Not an odd function, but an odd degree function, right? We can say that the left end behavior, x approaches negative infinity of f of x, is going in the other direction. So this is going to be negative infinity. Right, so hopefully this was helpful, right? In our next video, we're going to be talking about our first derivative test that we can use in order to identify critical points to find our minimums and maximums. So pause the video here. If you do not get to the next part because it's the end of the period, then we will go over this together as a group.